Good morning and good afternoon, everyone. This is the Blueback Rocks Velocity version 1.0 webinar. So we will start right away. Welcome, everyone. And please just let me know if there is any problem with audio or visuals, assuming everything is running fine. So we start. This is being recorded. So this presentation will be also made available later on. So this is the Blueback Rocks Velocity application that we have just released. So to let you know, we're trying to solve one essential need inside the petrel velocity model building workflow, which is the ability to see the data that will be used in your velocity model. So when we started designing this application, this is very strong feedback we got from many of our clients. So what are the main characteristics of Rocks Velocity? We made it to be easy to use, so meaning no convoluted workflows. Designed the interfaces specifically so that they just display the required type of data. It delivers very fast and direct access to well velocity and seismic, what we call pro velocities, processing velocity data. And it is designed to allow users to assess the quality of velocity data within minutes. So for version 1, this is the scope of the solution, delivering the ability to visualize and understand velocity trends very fast, and this coming from well data and also from seismic processing velocities. We can then proceed and extract and map layer velocity parameters such as V0 and K in the case of a linear increase with depth, but also interval velocities and average velocities. So we offer also some functionality to calibrate seismic velocities to well velocities. At this point, you don't need to build any 3D grid model to do that. You can do that right away in this application. Then ability to calibrate the velocity model with well markers, compare that to the well tops and reduce the differences. The idea is understand velocity parameters before going and building a model. So what sometimes is happening is you build a velocity model in Petrel. Maybe it looks good, but when you start looking at the details, then you may realize that velocities don't look as realistic as they should. In this application, everything comes right away into the front, and you have a direct way to assess the situation. All the results that we produce can be used and shared, if you want, directly within the existing petrol velocity model building process. So let me go just pretty fast through the different options, first as a PowerPoint, and then we go to a live demo. The application is built in a sort of logical way from left to right with specific panels or tabs where things happen. In this case, you define here the input data where well check shot data is being loaded to the application, as well as if exists stacking velocity. Everything is displayed right away in the location map. So here you can have already a very fast overview of trends and outliers in your input data. Next, there is a conditioning step. If using seismic velocities, this data needs to be calibrated to well velocities because of well-known problems or differences between, there is an anisotropy effect between well velocities and seismic velocities. So then we provide the necessary tools to understand this situation and decide what strategy to follow in order to achieve a calibration. Once this is done, then you build also your layers and you define markers and associate markers to the main surfaces, which can then be used to also produce useful tables with important information about velocity and crossing points between well trajectories and surfaces and so on. So that's quite useful to understand the quality of the input data. This would be the main tab where most of the workflow happens. It's where you estimate what type of model you will define looking at the data, not just guessing what it is behind it. So you will display and plot the velocities and then try out different parameter models like linear velocity, increase with depth, or interval velocity, have the ability to, if necessary, edit parameters, and then QC some differences of markers against surfaces. Once this is done, then we offer some displays about the optimization of residuals. It is known that because of the nature of this problem, it's impossible to find a single solution. But you would like to get into a best fit solution for your specific case. So this type of plots will help you understand the situation and maybe change your strategy in defining velocity models. And then finally, the output results. Once you've done some work, then you're able to save data in Petrel, and this is done in a way that it can be done interactively and also coming back and forth, so that you can test different what-if scenarios, changing some velocity parameters and looking at the impact of depth conversion, for example. There's options to save the calibrated velocities from the seismic and so on. So we will go through that later on in more detail through the demo. It is, as I mentioned, fully integrated in Petrel. So here an example of results showing in surface in time converted to depth and the equivalent of the interval velocity map, plus the points with the corresponding velocity values. So it is like any other Blueback application, tightly integrated in Petrel. Saving the velocity model can be very useful. At this point you would save average velocity representation of the calibrated seismic velocities. Using the Blueback toolbox, for example, you can convert this easily into a seismic volume and then use this right away in the advanced Petrel velocity model building process. For example, we got many questions from clients asking about 2D surveys. We support 2D surveys as well. Once you load this information in Petrel via ASCII points using some of the existing loaders, and these points exist in the Petrel system, then we can easily access them. This is an example here from the North Sea of the Barents Sea. It's a large regional project, all regional 2D lines, and the points you see there, they are all velocity locations. So we can also satisfy this workflow, which we believe is also important specifically in North America as well. So this is what Rocks Velocity is about, but now let's go and change the mode and go back to something more live, which is Petrel. And I will start now running a demo. Here we have already Rocks Velocity. As probably you know, all our applications are launched out of the marina environment, and here you have the Blueback Rocks Velocity. Once it's installed, then it shows up as one of the items that you can start. So then you start and you get to this interface. Here is where you would select, for example, all the possible wells that you have in your project. In order to show up in this list, we require that you have defined for every of these wells a proper checkshot object in the Petrel project. For a later version, we will probably expand this to support other time-depth relationships as well. But as of today, we require this to be a checkshot object. So then, as soon as you select those items, they show up in this base map here, and immediately also you can have a display in the velocity crossplot. So highlighting any of these wells responds with a highlighted red curve, which is corresponding to the well. On the other side, it is also possible to select, for example, any well from this display. So you see here something that could be like an outlier. So if we highlight this one, we see this is this well a bit far away in the south, and that next one here would be this Frodo well, which is also sort of more into the south side. So it might be this is not a real a problem, but it is something changing in the layer going southwards. But right away, just this display can deliver a lot of information about what is going on in your field. Like, for example, the way these check shots are displaying are giving already information about the behavior, for example, between the upper part and here. So it's already giving us some hints about what type of layers we might have to define here. So that's just the loading. I will come later and talk about seismic velocities. For the moment, I will just go and do this workflow without seismic velocities, only well velocities. Next, we are required to define a table, which is a similar stage as in Petrel velocity model building. In this table, you define your main horizons, the ones you want to look at. And the nice thing about this is that this interface is context sensitive, in the sense that you don't need to go to the large Petrel tree of a project, but it is enough if you do this from here. It will only show you the related objects. It's context sensitive, so it makes life easier. So here you define the time surface, and here you would define the corresponding marker, if there is one. If there is no marker, fine, you don't need to define one. It's only this little sign that warns you, okay, there is no marker, but it's the way it is. So once this is done, again, now we can go layer by or surface by surface, and here automatically we build the corresponding layers. So we build automatically a reference datum layer to the first defined surface, and so we can, for example, collab these tables. And as mentioned before, these tables give lots of information about what is going on with your data. It's easily to sort them for any of the columns, but here, for example, we see that for the Nori surface, all these wells here don't have a marker defined. This might be correct or not, but this at this point where you could go back into your interpretation and check if this is the way it has to be, or if there is a good reason why there is not a marker defined for this surface. Then it gives you information about the time where this surface is crossing the borehole path with the surface, but as there is no marker, there is no information. But we have, of course, in other cases, that borehole with a marker. So then we can compare the difference in time about those. So this is already giving you some interesting information about differences between time surfaces and markers, giving an information about related check shot quality, for example. And then we derive the corresponding average velocities at this stage. So this is all information related to the surface. If we call up a table like this in terms of a layer, so this information is more related to thicknesses. So here we compute the thicknesses out of the wells and the corresponding thicknesses out of the surfaces, and we compare the differences. In the case where you have a yellow or green or a red mark, it is because, like in the Saruman well, there is a too big difference in the thickness. Something is essentially wrong. You should go back and check that well, that marker. Why is that such a big difference between the thickness of the computed by the well and the thickness computed by the surface? And you can see these things right away before committing anything to a more complex model. If for some reason you would need to save this for later, it's easy to highlight that and copy this into the memory of the system and share this, for example, with Excel for other purposes. So we have now defined our layers, we have defined our surfaces, so I will now go to the next step, and here is really where we will start working for define our velocity parameters. So we can go layer by layer, so we are highlighting the first one. In this case, I'm starting with everything being interval velocities, which is fine. So I can display the interval velocity map and a corresponding residual of the values if I have some. As you see, it's quite a large interval here, or layer if you want. So you can map this as an interval velocity, so selecting every different location will highlight the different positions here where we have velocities. But you could say, well, I rather would try to map this as a linear velocity trend, in which case then we do our computation for the linear regression parameters for each well, and we compute the B node and the K values. And this one can also be displayed in this plot, either the B node values or the K values, depending on what you want to see. So this gives you right away an assessment of the quality of the data. Here is where you would immediately spot, for example, outliers in the data. If something is not correct in the trend, or something is changing too much. For the second layer, which is a small one, a very thin one, and where we have this higher velocity part, for example, I wouldn't go for a linear increase, but I would rather stay with an interval velocity map, which is what I'm displaying here. Then for the next layer, I go and define again I could define a different model. And here we have something interesting. We have a cross plot which shows the layer midpoint depth and against the interval well velocities. And there was a method developed in the 70s that became very, very popular. It's about estimating velocities out of this layer midpoint trend, which we have calculated here. So I display now the standard deviation, which is pretty small and it's close around the data. So this is telling me data is pretty much linear, which is very visible. In such cases, then it is possible to define what we call a midpoint trend. Again, it was a method that was very much used in many places. Be careful if you want to use this method and your data doesn't show up linearly in the specific layer. If it doesn't show this type of strong linearity, then you shouldn't apply this method. Okay, but it's one of the very well and established methods in the industry. So for the next layer going down, again, I think I would, you see here now I have a wider distribution of the data. So I think it's better maybe still to stick with a normal linear velocity approach. So I have defined now different parameters for my layers. So I have now a complete description of my instantaneous velocities. Then I'm ready to have an initial look at my the differences in depth that I may enter because of the modeling aspects that I'm selecting. And it's about now saying, what would I like to do? Do I accept these possible differences, or would I like to go and maybe try to optimize these differences? This we can do later. At this stage, I could go now and say, fine, I would like to create some results, which is what I'm going to be doing now. So I say, for example, this name, and I will create a folder where all my surfaces are going to be depth converted. I will do that right away, take maybe a minute. In the meantime, we can say some words about this part. I'm also able to create logs out of this process, like instantaneous velocity logs, so basically to reflect the status of my model, my velocity model for each well, and also average velocity logs. I could also save my surfaces as points in the case I would like to, map them outside using a more sophisticated mapping approach, kriging, co-kriging, whatever. Interesting, later on we will talk about this, saving the calibrated seismic velocities. So I have some results for now, which we will display. Here is our folder, webinar 2, and we have here a depth window, 3D window. So I'll just go and display, for example, Balin, which I see here. Let's give it some color. So we have now our depth converted surface, which is fitting our markers pretty good. So I could display the whole sequence. Going now on, the last one is the flank of the salt. This is an example of somewhere in the Gulf of Mexico, by the way. So our application deals also with deviated wells and does the correct computations based on the deviation, which is something not very simple to achieve, but it's done, so we do it. So this would be now first approach of depth conversion using pure wells. Coming back, I would now say, okay, let's go and add some more information. Let's use seismic data. So if you have seismic velocities, there's two options possible. We can use 3D seismic volumes. In many cases now, velocities are being delivered by processing centers as a seg-Y volume, so we can read and parse that information as well. And we offer an automatic way of resampling this, because in some cases it's just a lot of 3D interpolation inside, and the real information is not as dense as we would like it to be. So it's in lieu of saving also some memory and CPU, it's important to do a decimation of the seismic data if necessary. We do that on the fly. Now I'm going to select a set of points like this. So immediately it's red, so if you would like, I can display those points in petrellas as usual. So they are here. For this I need to change this to time, So when I display that, it's that information we have at this stage. So we're just reading this now into Rocks velocity. So we have the grid of velocity locations now together with the wells. There, right away, you see a very important plot, if you want. Immediately, you have access to lots of information. It is sometimes you would like to concentrate and see, for example, here, what is this? Where is this location? It is there, where this red cross is, or maybe select any other one, you know, which allows you to immediately see and spot potential outliers or problem zones and so on, and that together. In some cases now, when the data is as dense as it is now, you could decide it's much better maybe to reduce the amount of data, so I filter it out to the area covered by this polygon. So I see only what it is around this well, and in these few velocity locations highlighted here that are displayed in the map. So then if I go to another location, for example, I could move this polygon and then get a view from that side. So let's move on now to our surfaces. And now I have a different type of display. We have now, and this is what these circles mean, collecting information around each borehole to calculate the interval velocity of the well against the interval velocity of the seismic, and then we estimate the closest locations within this radius that is defined here to define these points. This gives us the ability now to compare well velocities against seismic velocities and then define a strategy for well velocity calibration. In this case, we're generating for the first layer these factors, and we're mapping them using a convergent grider. And in this map, basically, we are defining what's happening between well and well. And so here you see in gray the original data, while for the first layer, which is in that part here, we see what the calibration has done. And so we are comparing the green, which is all the wells, with the yellow, which is the velocity location. So we have now moved the velocity of the seismic closer to the wells. That's the exercise of the calibration. And then we can do this for each of the layers, in this case going down and doing the same exercise. There's several methods I could select. I have, for example, here also I could try to use like a regression out of this curve. Sometimes it is a valid approach. In some others you see that it doesn't bring maybe additional value. But the good thing about it, this is very, very interactive. As you see, we are not building any complex 3D grid here to do integration of velocity values with wells. It's just this application doing this in a very interactive way. If you would like to go and do your own mapping, you can save this information, these points, and then later on reassignment using a map that you have done, for example, using kriging or co-kriging and so on. So once this step has been done, so we say we have calibrated our wells. You could also say in the lower part, it's maybe not necessary to do any calibration at all. We have so much uncertainty, so much noise anyway, so it is maybe pointless. So I will leave it like that. So I will calculate my regressions, and I go now to the velocity analysis window. So now I have again everything all together, so I can work again. So here, as we said, I would prefer to go with a linear velocity, while in the second I would prefer to stick to my interval velocity. So, but now I'm looking at a complete integrated map, including wells and seismic velocities. Here again we have an interesting area which you could say, is this real, is it true, or is it just noise? You see it's just far away from the whole trend, and if you see the well here, it's showing us a different value. It's showing us something like 7.3, here the same 7.3, and here we have like 7.7. So I will change that to 7.390 to say something, and you see this is updated, and I will do the same here, 7.390, and this is also updated. So basically I am correcting for some outliers in the data that I see before committing to a depth conversion. So that's a lot of information now. And here again I would say it's better we don't map this as an interval velocity. I prefer to go and to do a B naught and K approach in this case. So again, this doesn't change much. It's the same. It doesn't imply new. This is only based on markers and the well data. Now I could depth convert my surfaces again. I will also save the instantaneous velocity, so I can show that to you, and we can save our calibrated average velocities in this folder, and also our depth converted surfaces as points. Here we could also save the different attribute maps like interval velocity or V naught or K maps. If we do that, we can assign those right away in the Petrel velocity model building process, for example. So now I'm generating these outputs, and they're going to be well, written in the Petrel tree or in the Petrel database. So it's done. So I can go back now. So this is our previous model. So it's not overwritten. It just creates a new version. So I will just turn off. And that was the previous one that we generated before, only using well data, and now it's the second one used well data plus seismic. And you see there is a difference, as expected, and on the markers the information is quite similar. However, way far away from the markers, now the trends are driven by whatever velocity map I've been doing, and in the case of the seismic, it shows that's a bit higher, which is probably a bit closer to reality, because in this first case I was just guessing or extrapolating my velocities without any further knowledge, while in the second case I'm using the seismic to drive this extrapolation. That's why we have a difference here, no? But that's the nature of this type of process. So we have again produced our results. I was mentioning that if I have, let me just see if I can get to the right function window here. Yes, and as you see, that's what I have saved. Before it is saved as wells and as logs. So I have an average velocity log, and here it is saving my instantaneous velocity. So this is the linear increase, this is the interval velocity, this is the linear, and so on. So this I can use for later comparisons with real data, or I can reassign that for further depth conversion processes. So that's an example of how things are saved in Petrel. So let me open a new 3D window in time in this case. Here I just want to show you we have saved also the calibrated seismic velocity points. So also we have saved the different, this is the results basically as points including wells and seismic velocities. So here you could say, I will use my own grading technique here, or I can use this for further quality check. But more interesting than that is this, where now we have the calibrated interval velocities, the original interval velocities, and the derived average velocities out of this process. So if you convert this set of points using the Blueback toolbox as a velocity cube, you could be using this in the petrel velocity model building process as well. So this more or less closes my demo. Back to our presentation. Here is where we have, back. We saw what Rocks Velocity is about, designed to help users to understand the data that is going to be used for velocity model building. It is demystifying, opening this process. It's opening that black box that has been there for a long time, where you had to build a velocity model and you couldn't see your data. It's completely integrated in Petrel. It's no need to, as you have seen, exchange, move, copy anything. It's just there. Clients that have started using these, and we got a lot of, I would say, pressure to start using this even when we were in beta. From Australia up to the far North Sea, they have been very satisfied with the efficiency that they bring, especially because they could identify what is going on with their data so early in the process. It is available at the Ocean Store right now, and this leads me to the roadmap. We have already version 1.1, which is entering final regression testing, and we're targeting this for end of January, with a few little enhancements and stabilization. Then we have already some plans for 1.2 version, which we are targeting for around March this year. And these are a few points that I have listed, like defining K as a constant value. We have also good ideas on enhancements for the depth optimization workflow, ability to mute bad players. This has been one of the first points raised by our Houston office, Rene at this point. Then we add the ability to define manually control points for grids using the graphic interface, and we will be able to create average and interval volumes as a seismic right away, and it's also further performance enhancements. Also, at this point, it's a longer term view, and we're calling up for any major or interested user, client, who would like to sit with us in the driver's seat. It is an early application, it's version 1, so you have the opportunity to sit on our driver's seat early on and drive the direction of the product. So things we're talking about for a longer term as adding uncertainty, automation for blind wells, ability to handle multi-surveys, add more velocity functions like non-linear, law of fast, and so on, and supporting complex velocity models. So those things are already in the under consideration. So this brings up to the end of our webinar presentation. And at this point, I would like to first of all thank you, all of you, for your attention, and open the stage for questions. If there are any, please let us know, and we will do that. Is any question around? So we don't have any questions, looks like. So, well, thank you for attending, and we will have this presentation shortly available for you to download on our servers. Okay, thank you very much. I think it went well, but ich hoffe, ich habe alles richtig gemacht hier mit dem Enzo had a question, yeah. So I say stopped. Allo, 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 test, 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 allo, 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 test. Allo, 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 test, 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 allo, 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 test, 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 allo, 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 test, 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 test. Allo, allo, test, 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 allo, allo.